Hi everybody, this is Dr. Burke and we're going to do mass on a spring simple harmonic oscillator. And this is an experiment you can actually do. What you need is a spring here. These are pretty much, you can get these at Ace Hardware if you feel like you can go and get one. And you need some mass, and you could get a plurality of different masses. This one here is 2.5 pound from a barbell, and you could sort of ignore the mass of this aluminum hook I have mounted on here through the hook has a threaded bolt on it. The hook itself is basically a bolt with a hook on it, a threaded rod with a hook on it. And I've got nuts on either side with washers so I can grab this thing. And then you need a spring here, a spring. So the first thing to do is to do this experiment, and you could do it with many masses. I'm going to do it for one, and then you can go do it with 100 if you like. But my write-up was real simple. You can even do the write-up without even looking at the this video. But hopefully you'll enjoy this video. So the first thing you got to do is measure the equilibrium length of the spring, and when I do that, I bring it over here to a meter stick. And I don't know how well you can see that. It's about, it's a little bit difficult to see exactly, but it's around 12.3 centimeters, which is 0.123 centimeters, rather. And so we have the equilibrium length of the spring. And then the next thing is you want to hang a known mass on here. This mass is 2.5 pounds. And the 2.5 pounds, if you multiply it by 2.2 pounds or kilograms, I screwed that up, didn't I? Here's a standard error. A kilogram is 2.2 pounds. So this should be 1 kilogram is 2.2 pounds. So if you take, so 1 kilogram is 2.2 pounds. So if you take 2.5 pounds and divide it by 2.2, you'll get the number of kilograms of this mass we're going to hang on the spring. And I only have two hands, and I got to hold the camera with one. So basically, if I take this mass and hang it, hopefully you can see that the spring gets longer. And with this 2.5 pounds on there, this spring stretches to be to a length of 43 centimeters. The equilibrium length was 12.3 centimeters. So just by hanging a mass on this spring, I can get an estimate of the spring constant. Now, it's really an estimate because the spring constant is different the more you stretch the spring. And really, but we're going to sort of get an average spring constant throughout that totality of that stretch. And so with the mass hanging on the spring, the force down is mg, and the force up is the spring constant times x. X is the change in length. So when mg is equal to k delta L, the spring constant is mg over delta L. And delta L is the 43 centimeters minus the 12.3 centimeters. If you take those and subtract them, you get 30.7 centimeters, which is 0.307 meters. So the spring constant is actually mg. M is the mass in kilograms. I'm going to have you do the calculation. The mass is 2.5 over 2.2. That'll give you the mass in kilograms, and that number goes in this. That number goes in this equation here for m. G is 9.8 meters per second squared, and delta L is this 30.7 centimeters. Now in your lab write-up, you're going to redo this calculation with different numbers. Okay, so you're going to get a number here for the spring constant. And once you have that spring constant, if we hang that same mass on there, if we use the same mass, and let that mass hang there and bob up and down like that. You can see it bobbing up and down. We can measure the period of oscillation. And the theory for the period of oscillation is 2 pi over the square root of k over m, or 2 pi times the square root of m over k. Again, m would be the number 2.5 over. So once you have the theory calculated, you can do an experiment and measure that actual period. So what you do is you take your mass on your spring. The mass is it's about a kilogram. It's 2.5 over 2.2 kilograms. And let it undergo oscillation. So you guys start your stopwatch now. I'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop your stopwatch. And that's the time it takes for it to oscillate 10 times. So if you divide that number by 10, you'll get your experimental value for the period. And you can compare this number to the number here. If you want to, you can just count the seconds on the time code of the video for the time for 10 periods. Divided by 10, you get this number, and compare it to your theory. Now, again, I got this at a hardware store. I got this hook with a threaded rod structure on it, where I could and nuts, and I could grab the mass. You can get many of these springs at a hardware store. And you can try different springs and different masses, and you can do this mass on spring oscillations. And the write-up I gave you is quite simple. So I think that will enable you to do this experiment. And it's fun because you can actually get all these items at a hardware store, and that's pretty cool. Okay, so. Again, repeat this experiment. You can get your own materials if you want. I think the spring cost me $2. This hook probably was I don't know, a couple bucks. And then these kind of weights you can get anywhere. Your neighbors probably have barbells, and they probably have 1 1/4 pound, 2 1/2, 5. And 10-pound weights that you could use. You can get a stiffer spring. This one's pretty loose. Now, delta L was really big. The equilibrium length was L 12.3, and this mass stretched at 43 centimeters. So delta L was pretty big. So that's going to be an approximate value for the spring constant, because really the spring constant would be the system is linear only for small displacements. We got a pretty big displacement, but you'll find out it's not too bad of a approximation. Give you a pretty good agreement between theory and experiment. Okay, get this lab done and get on to be studying your lecture so you can do well in your final, and I'll talk to you soon.